Now, let's look at collisions. Collisions. Collisions are when two things collide, and basically we want to calculate their final velocities. That's the idea. So there are several types of collisions: elastic, inelastic, and completely inelastic. Okay, so the idea is when two things go toward each other, and then, so that's like before, and then after they're kind of going back their own way, like that. Okay, so like two billiard balls like bouncing off of each other. So that's a basic collision, and if we know the initial velocities and the masses, we can figure out maybe the final velocities. But we need to know what type of collision. An elastic collision means that no energy is lost in the collision. So kinetic energy is conserved. It's conserved because that's the definition of an elastic collision. In other collisions, kinetic energy is not conserved. So it's not the case that energy has to be conserved in all of these types of collisions. It's just a very specific example, a subset of all the collisions where kinetic energy happens to be conserved. Completely inelastic is objects stick together and have the same final velocity. So what does that mean? So that's the example of, that's what I want to start with, is a train car bumping into another train car. And then after they stick together. So it looks like this. Okay, so that's all, we'll start it all afresh, after erasing. But that's the concept. They stick together and they have the same final velocity. That's considered a completely inelastic collision. Now, what is common, I didn't say the main point, which is that during collisions, momentum is conserved. So that's really the main point. Like I said, we defined momentum to be m times v. What does that really mean? It means that m times v is a useful quantity, and it's useful because it is conserved. Just as kinetic energy is 1/2 mv squared. That's a useful quantity because it's part of conservation of energy. It just happens to be a quantity that when you combine it with other types of energy, it's conserved. mv, I don't have it on here, mv is a useful quantity because it itself is conserved during collisions. All right, so let me erase and we'll do an example of two train cars. All right, so this is conservation of momentum P final equals P initial. Now I'm writing those as a capital P, although it's hard to tell the difference here. A capital P means the total momentum of all the objects in the system. So, so let's just say these are 1,000 kilograms. I'm sure they're more than that. Let's make it a different mass, 1,200 kilograms. Okay, so this one's moving at a velocity of 3 meters per second. They connect together, and then what's the final velocity? So this is like initial, I could say before and after, or initial and final. So that's the before scene. The after scene is okay, they're connected together. Because they're connected together, they're moving at the same final velocity. And what is v? That's the question. All right, so basically, to solve it, we just say, P final equals P initial. I could write it as, I think I'm going to write it as initial equals final, just so I can do the initial first. P initial equals P final. There's no really way to write it. There's no reason why you should write it that way or this way. Okay, what is P initial? That's the momentum of this car plus the momentum of that car. This one is stopped, by the way, initially. So let's put it this way, M1 V1 plus M2 V2, and I'm going to add initial, 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 equals, now they're connected together, M1 plus M2 V final, which we tend to write as a capital V. So that's not really an equation that's on the equation sheet, that's something you should kind of know, like you should be able to figure that out from P initial equals P final. What we're thinking is, all the initial momentum of everything, that is the initial momentum of this plus the initial momentum of that, added together equals the final momentum of the whole thing, which in the case of an inelastic collision, they are stuck together, so it's basically both masses moving at the same speed. The fact that they're stuck together pretty much defines it as a completely inelastic collision. All right, let's just put in the numbers to get the answer. So, 1,000, moving at a velocity of 3, plus the momentum of that, 0, equals total masses, 1,000 plus 1,200 times the unknown V. And now we can get V. So, 1,000. Now, by the way, before you get the answer, you might want to use your intuition. What's going to happen? How fast could it possibly go? It can't go faster than 3 because this thing by itself is moving at 3, and basically you're just adding all this mass to it, so it's going to slow down some. Well, how much will it slow down? If it was 1,000, maybe it would slow it down by half as much. You can kind of use your intuition to think what it might be. Now, sometimes one's intuition is wrong if you're not familiar with the equations, but it's always a good idea to take a guess and see if the answer seems reasonable. But let's get the answer and see. So 1,000 times 3 divided by basically 2,200. 1,000 plus 1,200. Yes. So I get 1.36 meters per second. Okay, so that does seem reasonable. Less than 3, it just slowed everything down. All right, so that's a basic kind of train car problem involving a completely inelastic collision. All right, next we have to look at, before I do that, let's look at the kinetic energy and see what happened. I wish I had more room, but we'll just squeeze it in here. Okay, so usually the problem ends here, but what I want to do is compare the initial kinetic energy with the final kinetic energy, and let's see what happened to it. So there's no question yet. The question, I'll give you the answer, and then we'll look at the question. So there's no question here other than what happened to the kinetic energies. So 1/2 mv1 initial squared, and then kinetic energy final is 1/2, that's m1, m1 plus m2 v big V squared. All right, so that's 1/2, m1 is 1,000 times 3 squared, and then 1/2 2,200 times 1.36 squared. So let's see what we get here. (1,000) times 9 divided by 2 is 4,500. Joules. That's what we started with. What do you think? What's your guess to see what we finish with? Should it be the same number? Should it be more? Well, the answer is it can't be more. And we expect it to not be the same number because it's an inelastic collision, but let's get to that. 2034. I'll just put the whole number. Look at this. 2034.56. Isn't that nice? 23456. That's a nice number. 2034.56. Okay, kind of fun. Anyway, so the point here is we lost kinetic energy. Where did it go? So we started out with 4 to 500 joules, we ended up with 203.456 joules. So we lost kinetic energy somewhere along the way. So that is typical of an inelastic collision. In an inelastic collision, there's no guarantee that, that kinetic energy is conserved. The conservation of kinetic energy is consistent only with applies only with a completely elastic collision, or just what we call an elastic collision. So for an inelastic collision, or in this case a completely inelastic collision, we do expect kinetic energy to be lost. Where did it go? Generally, when things stick together, there's some sound. Sometimes there's some deformation of the materials or movement of parts, to make it happen. Usually, those answers are somewhat unsatisfying because you can't really see where the kinetic energy went. But it's there somewhere. Like somehow kinetic energy was spent in sticking those things together. There's always some noise, vibrations, mechanical vibrations, that kind of thing. So that's just an example. So the question would be, I told you I'd give you the answer, then we'll make a question out of it. The question might be, how much kinetic energy is lost? How much Ke is lost? All right, so let's figure it out. Delta Ke equals Ke final minus Ke initial. So 2034.56 minus 4500 is, now let's, we get the negative sign, but don't just immediately erase it, and let's think of what it means. Negative 2465. Okay, that's the change in kinetic energy. The change from beginning to end was negative, so that means we lost. So 2465 joules are lost. So basically, the change is a negative number. The amount lost is the amount of the absolute value of that, the positive number that is lost. Okay. So this part, the whole analysis of kinetic energy, isn't always part of these problems. Sometimes it's added on as like a part B. But basically, it just shows, it's there to show you that in an inelastic collision, you don't get kinetic energy conserved. All right, now let's look at elastic collisions. Okay, here's a case where we have M1, V1, and I have to write initial, head-on collision with V2 initial and M2. Okay, so that's before. And then after, we have then they collide and they go the other way. V1 final and V2 final. All right, problem is now we have two variables. Like basically, if you know the initial conditions, the question is usually what are the final velocities. We have two equations. Or I'm sorry, well, we will have two equations, but what I meant to say was we have two variables that are unknown. So how can we find that just from momentum? So conservation of momentum will give us this. Will give us M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. Okay, so if we know all the initial stuff, we're still missing those two things. So we don't have enough information. Well, we don't have enough equations, basically. We have two variables. So basically, if you have two variables you're solving for, you need two equations. What we need is, don't forget, this is an elastic collision, so that means that we need to consider kinetic energy. So, since elastic, Ke is conserved. So now we have KE initial equals KE final. All right, so that's going to give us 1/2 m v1 initial squared plus 1/2 m v2 initial squared equals 1/2 m v1 final squared plus 1/2 m v2 final squared. So the way you would solve this problem is to solve both of these equations simultaneously. So if you look at it, it's a mess. Like if you solve this for v2, okay, that's all that stuff over there, and then plug it in here, you're squaring it, and it looks like it's going to be an algebraic mess. There is, however, an easier way to distill the equations, so you get a nice, easier equation to deal with. But theoretically, this is what's going on. We have two things for elastic collisions: conservation of momentum and conservation of kinetic energy, because that's the definition of what an elastic collision is, that it has conservation of kinetic energy. So what I'm going to do next is derive the equation from these two things, and then we'll continue on from there. So let me sort of consolidate all the information here. For an elastic collision, we have, so that's basically, we have M1 V1 initial colliding with M2 going at V2 initial, and then afterwards they rebound. So there's V1 final, and then there's V2 final. Okay, so as I said, we had conservation of momentum. So M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. And then we have kinetic energy, which is 1/2 mv squared for each of these things. 1/2 mv1 initial squared plus 1/2 mv2 initial squared equals 1/2 mv2 v1 final squared plus 1/2 mv2 final squared. All right, so basically it's just a matter of doing some algebra. So first we're going to play with this equation and make it a little nicer, and then we're going to use some information from here. So we're going to come up with a special equation that's used for solving these problems. I mean, like if you had to solve those two together, you could do it. It would be kind of an algebraic mess, but let's make it better. Okay, so first of all, what do we do first? First, let's get rid of all the 1/2s. And then, you know what I didn't do? That's M1, that's M1, that's M2, that's M2. No, that's not. That's M2, and that's M1. Okay, so again, this is the kinetic energy of ball 1 initially, there's ball 2 initially, and there's ball 1 final, and ball 2 final. Okay, so let's do two things. One is get rid of the halves, and the other is put the m's on either side. So all the m1s go over there, and all the m2s go over there. So we're going to have m1 times v1 initial squared, and then here's the other m1 minus v1 final squared. Okay, and then now all the m2s go over here. Ignore all the halves, they're canceled out. m2, so we have over here, we have v2 final squared, and bringing this over, so that's going to be v2 initial squared. Okay, that makes things look a little better. If you have we're going to factor these out. So basically, a squared minus b squared is equal to a plus b times a minus b. So that's going to be m1 v1 initial plus v1 final times v1 initial minus v1 final equals m2 times v2 final plus v2 initial times v2 final minus v2 initial. Now we take this equation and put all the m1s and m2s on the same side. I'm going to do this in red so you can see that it's a different equation. So m1, I'm going to bring that over here, and m2 I'm going to put over there. So basically m1 v1 initial minus v1 final equals m2 times v2 initial minus v2 final minus v2 initial. Let's see if it all worked out for what I want to do. V1 initial. Good. Okay, so if you notice, all of this is M1 times V1 initial minus V1 final. That is this and this. Okay, on the right side we have M2, V2 final minus V2 initial. So we get an M2 times V2 final minus V2 initial. In other words, if I divide this equation by this equation, I'm going to get rid of this, 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 and this. Because what you're doing is basically taking all this whole equation, dividing by this whole equation, and this basically gets divided out of the left side, this gets divided out of the right side. So if you want me to write that out a little more clearly, what I'm going to do is just sort of change the places. So M1 V1 initial minus V1 final. I'm just rewriting this in a different order with the multiplying. V1 initial plus V1 final equals M2 V2 final minus V2 initial. So I'm putting this first, times V2 final plus V2 initial. And then I'm going to divide it by this equation. I'll do that in red. M1 V1 initial minus V1 final equals M2 V2 final minus V2 initial. All right, let's start dividing. When I divide the left side, I get what's left over. V1 initial plus V1 final. When I divide the right side, see those are kind of, like I get like pretty nice. V2 final plus V2 initial. All right, so this becomes an equation that we use to solve elastic collision problems. So in the end, you have momentum and then this equation. So I don't know what it's called. I usually call it the elastic collision equation. Elastic collision equation. What it is, after all this algebra, it's basically a statement that kinetic energy is conserved, and we use the fact that momentum is, we use momentum conservation to help derive it. But basically, it's a statement of conservation of kinetic energy in an elastic collision. All right, so that's the equation. I think it's written like that in the equation sheet because it's easy to remember. But there's another form we can write it in which gives us some conceptual understanding. And that is this. If I put the V1 initial minus V2 initial equals negative V1 final minus V2 final. So you can convince yourself that that's correct. But what this shows, this is a difference in velocity between 1 and 2. So this is called the relative velocity between 1 and 2, and this is the relative velocity between 1 and 2 final. Relative velocity before equals relative velocity after. So that's kind of an interesting statement. That means if you're on one of the objects and you see the object coming at you, the relative velocity is sort of the change, the difference in velocities between you. It's sort of like how fast you guys are coming toward each other, and the relative velocity after is you're going away from each other at the exact same speed. That doesn't mean your initial and final velocities are going to be the same speed, but the relative velocities will be the same. So that's an interesting idea for an elastic collision. So how fast you're going toward each other is going to be equal to how fast you're going away from each other after the collision. However, there could be a change in, V1 initial is not equal to V final initial. Like they could have a difference of 2, and then they would still have a difference of 2. But that means, they could have increased or decreased in such a way that the numbers are not the same. However, the relative velocities are the same. So that's the concept there. So let me summarize here. After everything we've done, what we've done is derived an equation that can be combined with momentum to solve elastic collisions. V1 initial plus V1 final equals, I'm going to write it as V2 initial plus V2 final. I think that's how it is in the equation sheet. Okay, so that's all you need to know. So forget about everything we did. What you need to know to solve an elastic collision equation is this. You need to know that momentum is conserved and that this equation applies. And then somewhere in the back of your mind think, what is this equation? Oh, yeah, it had to do with relative velocities and kinetic energy. Like the concept's in there, and I'll let you use that as like a starting equation because we derived it, but still have in the back of your mind like, oh, that has to do with kinetic energy, rather than just thinking, oh, that's an equation you plug numbers into. So the concept is momentum, kinetic energy, both of these equations together. So now it's nothing squared, it's kind of very easy to solve. So basically, if you have the initial conditions, you plug in all those, and you have the masses, so you're looking for V1 final, V2 final, and here we have V1 final, V2 final. So we'll stop there, and that's about it for today.